So when you look at an exponential function, like this awesome swooping curve right here, you have to remember that it's playing by a certain set of rules. It has boundaries. Today, we're going to decode those rules. We'll figure out what you can put in, what you can get out, and what happens at the very edges of the graph. So let's jump right in.
Here's what we've got on tap. We'll start with the basics, inputs and outputs. Then we'll get into this cool idea of an unseen boundary. We'll see how that applies to something decaying and how the real world can actually change the rules on us. We'll also tackle a super common mistake people make. And finally, you'll get a chance to try it out for yourself.
All right, first up, let's talk about the most fundamental rules for any function, its domain and its range. You can think of these as the what can go in and what can come out of our little function machine.
So the domain is basically everything you're allowed to plug into the function. When we're looking at a graph, this is all about the x values. Think of it as the fuel for the function. What numbers are we actually allowed to give it to work with?
And the range? Well, that's what the function spits back out. It's the whole set of possible results, or y values, that the function creates. And we see those along the vertical y-axis. It's the answer to the question, what did we get?
Let's take a look at a standard exponential function, just like this one. See how the graph stretches out forever to the left and to the right? That tells us we can plug in any real number for x we can think of. So the domain is all real numbers. But now look up and down at the y-axis. The curve is always above the x-axis, right? It gets super close, but it never actually touches it. That means our range, our output, is all positive numbers. Y has to be greater than 0.
And that brings us to a really cool idea. This concept of an invisible boundary line that our graph gets closer and closer to, but just never crosses. This is what we call an asymptote.
So take a close look at the left side of this graph. What do you see happening? As we trace the curve and the x values get smaller and smaller, -5, -10, -100, what happens to the height of that curve? This shows it perfectly. The farther left we go, out towards -infinity, the flatter that curve gets. It snuggles right up to the line where y equals 0, which is just the x-axis, but it never actually makes contact. It's always just a tiny bit above it. So this is the key takeaway right here. That line that the graph is cozying up to is the horizontal asymptote. It's like a boundary for the function's range, telling us, hey, the outputs will get really close to this value, but they will never actually land on it.
Okay, so let's see this whole asymptote thing in action with a real-world example. This idea of approaching a limit is literally everywhere, especially when you're looking at things that decay over time.
Okay, imagine you take 300 milligrams of aspirin. Your body starts to process it, and let's say the amount gets cut in half every single hour. So after 1 hour, you're down to 150 milligrams. After 2 hours, 75. Then 37.5. Notice the pattern? The number keeps getting smaller and smaller, but it's never going to be negative, right? It's always a positive amount.
In this graph, it's a picture of that exact same thing. Just like the aspirin amount in our table, the value of this function keeps dropping. It gets closer and closer to 0, but it will never actually get there. The line y equals 0 is our horizontal asymptote again. It's the absolute floor for our function.
Now, in pure math land, the domain can be all real numbers. But what happens when we start applying these functions to real life? Well, the situation, the context, can actually change the rules of the game.
So let's take a look at Danielle's charity drive. She's tracking donations for 30 days straight, and the number of shirts she gets follows an exponential pattern. Okay, let's think about the domain here. The x value stands for the number of days. So, does it make any sense to talk about -5 days? Can you have negative time in this scenario? No way, right?
Exactly. It doesn't make sense. The real-world problem actually forces us to restrict our domain. Time can't be negative here, so the only domain that makes sense starts at day 0. And this is a huge part of interpreting graphs. You have to understand when the story behind the problem changes the mathematical rules.
And that leads us right into one of the most common mix-ups that people have when they're first learning about this stuff, especially with exponential decay.
I want you to think back to our aspirin example. We kept cutting the amount in half. 150 became 75, which became 37.5, and so on. If we could keep doing that forever, does the amount of aspirin in your system ever hit exactly 0? Well, mathematically, the answer is no. And here's why. With exponential decay, you're always multiplying a positive number by another positive number, like 0.5.
And a positive times a positive is always positive. The result can get ridiculously, mind-bogglingly small, but it can never, ever mathematically become zero.
All right, you've seen the concepts, you know the rules, you've heard about the common mistakes. Now it's your turn. It's time for you to be the analyst and read the story that a graph is trying to tell you.
Here we go, a brand new function. It looks a little bit different from the other ones we've looked at so far. So just take a second and really study its behavior. Where does it seem to be coming from on the left? Where is it headed on the right?
Okay, go ahead and pause this explainer. Based on everything we've talked about, I want you to try and identify 3 things: the domain, the range, and that super important horizontal asymptote. Just think, what's allowed in, what's coming out, and what's that invisible boundary line? Because really, that's what this is all about. The domain, the range, the asymptote, they aren't just vocabulary words you have to memorize for a test. They're like the grammar and the punctuation that let us read, interpret, and truly understand the powerful stories being told by these amazing functions.